And I got 20 minutes to make a video here. I'm going to see if I can crank these out. If I can't, I'm going to have to bail. So this is 4.2. I don't know why I drew a circle around that. That's weird, because it's not a problem number. We're starting at number 1. I'm going to do 1 through 25, odds, and then 31, 33, and 51 for good luck. All right, number 1, y equals natural log of 5x. So the derivative of natural log of whatever is 1 over whatever times the derivative of what's inside. That's interesting. So that's just 1 over x. That's the derivative of just plain old natural log x. But then you say, aha, that makes sense because by logarithm rules, this is the same as this, and that's just a constant. And when you take the derivative of that, of course, that's 0. So it should be the same. Cool. So how about y equals the natural log of 1 plus x. The the absolute value signs here are just because of domain compatibility issues. I'll talk about that more some other time. So that's just 1 over 1 plus x times the derivative of what's inside. All good? All right. How about y equals natural log absolute value of x squared minus 1. Y prime is 1 over x squared minus 1 times the derivative of what's inside. I'm going to go ahead and just put that on top. You could put it off to the side. That's fine. No simplifying that can be done there. How about this? Y is equal to natural log of x over 1 plus x squared. Not sure why they didn't put that one in absolute value signs, but I'll leave it like they have. So the derivative of natural log of whatever is 1 over whatever. Well, that would flip that over times the derivative of what's inside, which is low, d high is 1, minus high, d low, over low, low. And I don't know, you could leave it like that, I guess. I mean, I'm awfully tempted to do a little bit of simplifying here. On the top here, I've got 1 plus x squared minus 2x squared. That's 1 minus x squared all over x, which is 1 over x minus x. Something like that. Number 9. How about the natural log of x squared? So that is 1 over x squared times the derivative of what's inside, which is 2 over x. That's interesting. But then you're like, oh yeah, that makes sense because there's another rule that says if you have a power here, you can bring it out to the front. And then that would have been just this, right? So that works. Cool. Number 11, how about the natural log of x to the 1/2 power? Well, the derivative of something to the 1/2 power is 1/2 times that thing to the negative 1/2 power times the derivative of what's inside. Number 13, feeling some product rule coming on here. X, natural log x. Derivative of the first is 1 times the second plus the first times the derivative of the second. So that's just natural log x plus 1. That's natural log x plus 1. 15. How about this? Y equals, now log base 2 is no good because all of our rules work for just natural log. So I'm just going to do a quick, as I'm writing this out here, I'm going to do my change of base rule, which is going to make a natural log 2 on the bottom, and then I'm going to have x squared times the natural log of 3 minus 2x. So this is my change of base rule. This over this is the same as log base 2. That's important. It's a basic logarithm rule that you need to know. Let's see. That's just a constant. I guess I'll treat this like it's part of, I'll do like this is my first and this is my second in my product rule, and of course this is just a number. So the derivative of the first is 2 over natural log 2x, right? Kicking the exponent out to the front, times the second, plus the first, times the derivative of the second. Derivative natural log of whatever. You know, when I get more into the groove of doing derivatives of natural logs, I would recommend just leave that top blank when you know that you're going to have some chain rule, because then you just put whatever the derivative of what's inside, you can just throw it down there on the top. All right, that's good. Book probably like reconverted that back to log base 2 or something, but that's all fine. Let's see, number 17. How about x squared over 1 plus, now log, that means log base 10, so that's the same as 1 over the natural log of 10 times the natural log of x. I'm writing it this way because that's just a number, right, times that. I think that's easier to see what the calculus needs to do there. All right, so now quotient rule. Low, you can just write it like that here, like in its original form. Low d high minus high d low, derivative of that is 0, derivative of this is 1 over natural log 10 times 1 over x. One of the x's can cancel there if you like, over low low. And when I write that low low, I can write it in its original form, right? You could simplify that a little bit. Oop, physics. Where are we at? 19. The natural log of x. What an odd thing to do. Okay, so let's see. The derivative of natural log whatever is 1 over whatever times the derivative of what's inside. So that's it. No, it's not hard. 21, the natural log of tangent of x. Let's see, derivative natural log whatever is 1 over whatever times the derivative of what's inside. And let's see, if you turn that into sines and cosines, is there any simplifying that can be done there? Let's just try that. So tangent is sine over cosine, so this is upside down, so that's cosine over sine. And secant squared is 1 over cosine squared. So sure enough, one of those cancels, and you get 1 over sine times 1 over cosine. Well, 1 over sine is cosecant x. 1 over cosine. I bet the book got all cute and did it like that. That's one way of writing it. Not that that's not wrong. It's just, it is what it is. Cosine of natural log x. How about that? Cosine of natural log x. Let's see. The derivative of cosine of whatever is negative sine of whatever times the derivative of what's inside. Number 25, how about the log base 10 of sine squared of x? All right, so first of all, change of base. And then on the inside of this, really sine squared x. And I'm going to do that little trick where you get to move the exponent out to the front, because because I think that's going to make it easier. You can try it the other way if you didn't see that, and see if you get the same answer. There'd be one more layer of chain rule if you do that. Sorry, trying to go fast, a little sloppy. So the derivative of this, that is just a number, times, if you're thinking to yourself, wait, I thought the derivative of a number was just 0, but the derivative of a number times function of x, that stays there as that constant, just like the derivative of 3x is 3, right? Not 0. Let's see, there's my constant, and then derivative of natural log of whatever is 1 over whatever times the derivative of what's inside. So different ways of writing that. Suppose that's equal to cotangent, right? 2 cotangent x over natural log 10, perhaps. All right, 31 we're jumping to now, because that's what your math teacher said to do. Find dy dx using logarithmic differentiation. Ooh, what's that? All right, logarithmic differentiation is where there's no logarithms here, but I'm going to introduce log on both sides. And since this is multiplication here, that turns into addition. And since that's a power there, that can come out to the front. So that's the game. And then after you do that, arguably, it makes it easier to find the derivative. What's the derivative of natural log y? Well, that's 1 over y, but implicit differentiation, like last section, dy dx pops out. That's equal to 1 over x plus 1/3 times, that goes on the bottom, derivative of what's inside that. And then this, if you just want to know what's dy dx, well, dy dx is equal to y, which is the original function, right? Y equals this times this. That's how that game works. I think we're going to make it here. 33. Another one of those. Ooh, that's ugly. Let's see. So the first thing I suppose we should do is write it in the most, oh, you know what, that's already pretty calculus friendly. It's just that thing, that square root on the top. Just imagine that that's to the 1/2 power. So I think we can jump straight to this level. So if we take the natural log of y on this side, and on the other side I'm going to have 1/3 natural log of x squared minus 8. And then I have multiplication with this thing on the top. That's 1/2 natural log x cubed plus 1. And then division turns into subtraction, and there's no big exponent on that. It's just the natural log of x to the 6 minus 7x plus 5. Right? That's how that first step works. And then I have the derivative of this is 1 over y dy dx. That's equal to 1/3 x squared minus 8 on the bottom times the derivative of what's inside. Here, x cubed plus 1 on the bottom times the derivative of what's inside. And finally, x to the 6 minus 7x plus 5 times the derivative of what's inside. And then to write the final answer, you just have to move this over to the other side. So dy dx is equal to y, which is the original function, times all of this stuff. If you're wondering to yourself, you are. I know you are. You're like, wait a minute, can I do that thing, like that lazy thing that you just did with the arrows and stuff? Like on a quiz or something? Nope. Sorry. And then last, number 51, find the limit by interpreting the expression as an appropriate derivative. So what is the limit as delta x? You know, delta x, I'm not fooled by that. That's just an h, right? That's the little thing that's getting really close to 0. So I'm going to make that look like an h because that looks more familiar to me. Natural log of e squared plus h minus 2 over h. I replaced all the delta x's with h's. Okay, well that looks an awful lot like limit as h approaches 0. This is like an example or an instantiation of this. So the question is, what's the function? What's the x value? So it looks like my function is the natural log function. Right? You don't want to get ahead of yourself and say, oh, the function is the natural log of e squared. No, natural log of e squared is a number. The function is the natural log of something, and the something that's getting plugged in is e squared. So now, well, if this is the definition of the derivative, then, well, I can find the derivative of that. That's just 1 over x. So f prime of x is just 1 over x, and f prime of e squared is just 1 over e squared. So that's what's up here. So same thing here, except this one looks a little bit more like the other definition. Limit as w approaches 1 of natural log w. I'm going to put minus 0 here just to make it look more like this. F prime of c is equal to the limit as x approaches c of f of x minus f of c over x minus c. So what's the function here? It's the natural log function again. And the x value that we're plugging in is 1. Right? So can we do that? Yeah, of course we can. It's the derivative of natural log x is still 1 over x. We're plugging 1 in, so f prime of 1 is 1. That's all, folks.